Okay, well, thank you all for still being here. The stalwart crew hanging out to the bitter end. So I realized yesterday that I had mistitled the talk. That when Murat asked for the titles, I gave him a title. It was actually an honest title. It does represent the work I'm going to present this morning. But I realized yesterday that a much better title for the talk would have been this, The Third Age of Neural Computing. This would have been I just wish I'd heard of that concept before the titles were due. So the reason I think that we really are in the third age of neural computing, I'm actually going to tell you first why I think what the reason isn't. So as great as some of the technology is that was presented in this meeting, two-photon calcium imaging and serial EM reconstruction, using crowdsourced techniques and genetics and everything else, we're going to learn a lot from that, but I don't think that's the real basis for the third age of neural computing. And I don't think the answer is deep neural networks either, although I'm indebted to them for creating all this new excitement about neural networks. I actually think the third age of neural computing is at hand because I think we are converging on a concept of a universal cortical processing module. And so today, I'm going to stress a particular example or a prototype for what a cortical processing module might be. But what I would assert is that what we've seen over this meeting are several proposals for a universal cortical processing module, some of them today. I think for most of us, we probably would think of what Jeff Hawkins is doing and HTM as a candidate for a universal processing module. What I'd like to assert is that all of these proposed cortical processing modules are really in the process of converging, this process of evolutionary convergence, toward the same thing. I think there's a consensus in this room and throughout this meeting that all cortical processing modules are going to have certain common traits. And whether any particular module has a particular trait right now, it will eventually. And I'm going to try to emphasize this theme throughout the talk. So the particular universal cortical processing module I'm going to focus on here is a sparse predictive coder. We've seen some examples of this earlier in the meeting, but the basic idea of a sparse encoder, find my mouse. So the idea is I have a column of neurons, in this case a column of V1 neurons. Each of these neurons is tuned to a particular feature. You can see the features illustrated here. And the idea is that this column of neurons is going to compete. Each neuron in the column is going to compete with the other neurons in the column and also with neighboring columns. So these columns are implemented densely so they overlap each other. The receptive fields overlap. And so there's this process of competition where each neuron attempts to explain some aspect of the image. And in explaining that aspect of the image, it sort of prevents any other neuron from explaining that same aspect. And so that's what generates the sparse code. So rather than go through the math, I thought I would just show you a video of this our particular implementation of this algorithm in action. So you just saw these V1 neurons, these columns of V1 neurons compete with each other to reconstruct this particular image. And then in a moment, the image is I'm going to flip to another image, and you'll see the neurons recompete. So there's another competition. You can see that the pretty much the low frequency kind of diffuse features tend to come on first and account for kind of the gross aspects of the scene, and the details are filled in later. Maybe in the interest of time, I'll see if I can speed this up a little bit to the end. Let's see one last transition to the sports car. I want to get to this because I want to focus a little bit on, well, if I go back to the previous image, you can see that the sparse reconstruction is good, that much of the information in the original image has been preserved in the reconstructed image in the sparse representation, but some detail has been lost. And it's possible that the detail that's being lost is exactly the detail that we'd like to lose. Some of the blades of grass have been lost in the reconstructed image compared to the original image. Some of the gravel stones along the driveway and things like that. And we're going to see that theme repeated as we go on. So that's one property of a universal cortical processing module. I think that everyone would agree that it must have. It must be self-organizing. It must generate a good sparse representation of its input. It must generate a good encoding. And then it must also be self-organizing. It must be able to learn in an unsupervised way from any input data stream. And this is just a simulation I ran over the last couple of days on a somewhat larger S1 dictionary, just showing, starting with random weights, this sparse representation, the sparse predictive coding module is able to factor this, video. Well, it's not video in this case. It's these are images from the PASCAL database, but it's able to factor this database in a reasonable way, right? And it's able to factor, and it's probably better to go back maybe to this figure where the features are more converged. But so a cortical processing module to be worth the name should be able to factor the input, starting from a random state, should be able to discover that the natural basis for describing that input, consists of broad, diffuse features and grayscale orientation and spatial frequency selective features and color opponent features. And so this is really, I think, part of the enthusiasm for why we're converging toward a cortical processing module, that we've acquired now as a community this ability to self-organize in response to complex data and to break that data down, to factor it into its essential components. And so, I'll skip that. So the third property of a cortical processing module that we have to desire is that it be composable. It be something that we can link together into almost arbitrarily complex topologies. And so think of this as almost a sparse rack. So you've seen this kind of icon for a sparse autoencoder before, consisting of an input, some kind of residual error that represents your prediction error, and some kind of a dictionary on top. And we imagine that we have a rack of these components, a rack of these sparse autoencoders that we can link together into essentially arbitrarily complex topologies. And so the first topology I'm going to look at is sort of the simplest topology you would imagine trying to construct. I'm just going to take one of these sparse autoencoders and put it on top of the first one, right? I'm just going to take the output from the first one and feed it into the second one and see what comes out, in essence. So the first problem, so people have tried to do this, but as I'll get to in a moment, it's computationally challenging to actually, it sounds like a simple thing to do, to just put a sparse autoencoder on top of one. But in fact, the number of features that you have to contend with grows by a large amount, and the number of neurons to remain overcomplete also grows. So you can't really see those features at this scale, but so if I just blow up different parts of that mosaic just so you can actually see the details of these individual features, you can see at the second level now of sparse encoding, we're already starting to move away from just oriented edges and color opponent blobs. We're already starting to learn things that, and again, this is all unsupervised, this is self-organizing, but we're already starting to learn features that start to be more, well, they're more complex. I don't really know how to, we're seeing things like corner detectors, crosses, curvatures. Most of these cells seem to be very strongly end-stop. If there is an edge they're sensitive to, that edge seems to be, met with something of opposite polarity. So anyway, I should put these on, I don't know, like holiday cards or Christmas cards or something, these dictionaries. They're kind of beautiful. Okay, so I showed you the dynamics of the first layer of sparse autoencoding, and now I want to compare the dynamics of the first layer with the dynamics of this second layer, the second module I've added on top of it. And what we would expect is, since the second layer is generating a sparse representation of the first layer, we'd expect the second layer to be slower, right? There'd be some kind of delay in the process. And in fact, that's exactly what we see. So we're going to look at the reconstruction of the same 5 images. So the video on the left is the same video you saw earlier, and the video on the right is now the second layer of sparse reconstruction. Remember, this is using a much larger dictionary, and a dictionary of more complex features. And again, if you, it's probably hard to see from where you're sitting, but there's going to be not only a slowing down in the response, but there's also going to be a further loss of detail. So at the second layer of encoding, at the second level of this hierarchy, we're again losing fine spatial detail, and in some sense turning the image more and more into a cartoon version of the original image. We're moving towards a idealized sort of platonic version of the original image. And maybe to speed this up, I'll jump ahead again to our sports car. Well, I hate to lose the transition. It's so beautiful. Okay, so this is the S2 layer now. These more complex S2 neurons competing with each other to explain this red sports car. And again, you can see that whereas the grass is already becoming, you can maybe say, idealized at the S1 level, it's even further. It's becoming almost a uniform green patch at the S2 level, and that's true of the details of the roof as well. So, I can quantify what you just saw. What you saw was that the error, the reconstruction error presented as a percentage RMS error, falls pretty quickly. The image, the reconstructed image becomes quite recognizable very rapidly. You can see the 5 images. The error jumps when the image flips, and you see the error fall very quickly. But the characteristic time course at the second level is slower, and the overall reconstruction error is a little bit higher. The floor is a little bit higher. And likewise, if we look at the percentage of active cells, again we see a different dynamics actually here. We see that at the first level, at both levels, the dynamics of sort of sparsification is slower than the dynamics of image reconstruction error, at least for this implementation. And I assume that's because as the error drops, sort of the drive to the system goes away, and so there's sort of a more sluggish time constant that takes over, that governs the approach to the sparsest solution. And so that's one characteristic. But I think, but to me, the most important observation about the reconstructions you just saw at the S2 level are that although there are details being lost, there's a tremendous amount, the essence of the image has been preserved, right? The information about what you're looking at is still quite recognizable, even from that second level of reconstruction. Yet the algorithm is using more complex elements. They span a much larger portion of the visual receptive field. And so the hope is that at the second level of reconstruction, by factoring the image using these more complex elements but that also smooth out over fine spatial details, we're going to obtain a representation that's going to be more, that's going to support better classification, essentially. That we should average over small variations that are represented by small details, but still capture the essential features of the objects that we're trying to classify. And so as some preliminary evidence that that's true, so we did apply the second level dictionary to an object localization task using the PASCAL database. Now I'll just disclaimer right now, I'm not going to compare our results to the published benchmarks on Pascal, because we're really not there yet. But what I'm showing you are fairly representative examples. What we've done is we've taken each image and we've tiled it at two different resolutions, either a fine resolution, 16 by 12, or a coarse resolution. And this is because the objects in Pascal occur at very different spatial scales. And what you're seeing in the left column for each image is the ground truth supplied by the Pascal gods, right? That's what that's where that particular object actually was. And you can see in many images there are multiple objects. Couches are actually, sofas are a Pascal object, people are Pascal objects. So most Pascal images have multiple objects, and it's really so it's not a whole image labeling task, it's a localization task. And then in the right column you can see what I'm showing is I'm looking for, so what we did is we just trained a simple single layer perceptron, just a very linear classifier for each one of these output tiles, and it's the same perceptron, shared weights everywhere. So we don't keep any information about where we are in the image. And so I'm finding the highest confidence detection anywhere in the image for a given tiling, and then I'm going to, so for this image on the left, it turns out the highest confidence detection was in fact a bust. And so then I'm going to look and see, well, where else in the image did I have an above threshold detection for that highest confidence object? And so that's what I'm showing at the two different scales. And you can see we usually do pretty well, although you can see we made one mistake on the right here at the high resolution. We mistook this bicycle. The highest confidence detection was actually, well, it was actually a bicycle when in fact the object is a motorbike. And I can quantify that a little bit better and also quantify the difference between the information for object classification encoded by the S1 representation versus S2. So what the green and red histograms, we're in New Mexico, it's good, it's a good color scheme. So the green distributions are the confidence values for all output tiles that are inside a bounding box for the associated object. And the red histograms, the red distributions are the confidence values for the same output tiles when they're not inside that bounding box for that particular object. And here I've just listed 6 of the 20 Pascal objects. And what you can see is that there's more separation, that the confidence values are, ideally the red and green would be completely separate. There would be no Christmas. That would not be allowed. The red and green distributions, if they were completely separate, then we would have perfect classification. So we don't have that. But we do see that the separation is reasonable. So these higher level, so by generating a sparse representation, we do in fact achieve some degree of object discrimination. We learn features that do discriminate to some degree between different object categories, and that this object discrimination does improve, at least incrementally, as we move up the hierarchy. So that bodes well, I think, for the idea of this particular cortical processing module as being a candidate. So a student, actually Shenhua Zhang, who goes to school here in Albuquerque at UNM. He's a PhD student at the University of New Mexico in the Department of Computer Science. And so he did a very elegant study. So I kind of leapfrogged. I sort of jumped to a second level hierarchy, but really I should have told you first what just a single cortical processing module based on a sparse predictive coder can do just by itself. And so Shenhua conducted this study, and he really asked two, what I think of as very, very important questions. So the first question he asked, it is a question I frankly asked of a number of my colleagues and had trouble getting a clear answer to, was if you train in an unsupervised way a dictionary for sparse reconstruction. So I'm finding a basis that allows me to sparsely represent my data in some optimal way. But it has nothing to do explicitly with detecting objects. I didn't sculpt my features to permit good object. I just sculpted my features to do good sparse reconstruction. Does that in fact, sort of as a byproduct, lead to better object classification performance? And so Shenhua did an experiment using the Cipher 10 So these are 10 whole image classifications. The images are very small. And in fact, what he finds is that as a function of training, so starting with random weights, just with those random initial weights, he already finds that there's some degree of classification performance that those random weights support. But as he trains for minimizing sparse reconstruction error, in fact, the classification performance improves as well. So as you learn features that provide a better description of the manifold on which everything in the image is living on, you also, as a byproduct, obtain better discriminability. And since people always ask about, yeah, well, what's the state of the art? So at the moment, the state of the art for a single level classifier is, for a classifier consisting of a single hidden layer is about 73% for a sparse autoencoder and just under 80% really for the very best algorithm. So we're still have work to do. So a fourth property of a universal cortical processing module, again, of which I present this only as one of a number of candidates that I think are converging towards a similar, ultimately towards kind of the same global functionality, is the ability to execute on modern, on just the what's available today in the area of high performance computing. And so Shen Lundquist, who went to school just south of here, somewhere in the room, I think, at a great little technical school called New Mexico Tech in Socorro. And so he took our code, which is called Predictive. It's an open source code. You can download it and play with it if you want to. It doesn't have quite the documentation that would make that would facilitate that, but it is open source, and there is some documentation, and we do use Doxygens and things like that. So what he did is so Predictive already was an MPI code, so we took images, we cookie cuttered them, and we passed information along the borders to neighboring processes to pass whatever information they needed. And so what Shen did is he took this whole code base and ported it to a GPU. And he also, so what he realized is that there are really two kinds of convolutions you have to do in sparse predictive coding. There's a sparse convolution. So you have to generate a predicted image. You have to generate a prediction of your input. And typically that means you're going down a list of neurons of which only a tiny fraction are actually non-zero. And so that kind of convolution is actually best done in a multi-threaded fashion on a CPU. And so Shen implemented that using OpenMP. And then there's a dense convolution where you have to actually convolve over this residual error. And that Shen put on the GPU. And so what he wound up with was a hybrid execution model that used MPI to pass information among multiple machines, multi-threading to take advantage of all the cores, the CPU cores on a single machine, and then GPU acceleration to take advantage of that. And so this is an example of Shen running some code for his depth modeling, which I'll show you in a moment, where he's running in the on multiple GPU spot instances in the Amazon cloud. So this is 4 GPU spot instances, and I think this cost about, I don't know, about 25 cents. A 2-bit cores, if you want to call it that. So for 25 cents an hour, you can rent, an incredible amount of compute. And this is just available to all of us today. So why are we at the third age of neural computing? Well, because of CUDA and cuDNN and the tools that are available to us now to take these cortical processing modules and actually investigate them at scale is simply unprecedented, I think. This has never before been true. So I want to finish up with 2 applications. So this is work done by Wesley Chavez, who actually grew up here in Albuquerque and also went to school at New Mexico Tech. And the question he's interested in is action classification. So if you just looked at these 2 images, it would be very hard to tell who's swimming a breaststroke and who's swimming a crawl, at least unless you're a coach or something. But of course, if you actually play the video, you see immediately, what is what. And so the only way, we think, has been pointed out repeatedly at this meeting, to learn, to probably solve such a task is to utilize time. We have to also represent how features change over time in some way. And so we're going to take the exact same cortical processing module here. We're going to take the same sparse autoencoder, but instead of representing a single image frame, we're going to represent a sequence of video frames, a sequence in this case of 4 video frames. But it's the same, it's the same everything. We haven't done anything different, but just represent a slightly different input. And so this is the dictionary that Wesley learned. And so you can see that now he not only learns little oriented features, but these features now evolve in time over this sequence of 4 frames in a manner that qualitatively appears natural, appears like this would be reasonable explanation for the fate of these features. And so recently, Wesley applied this to 6 categories. There's a UCF, University of Central Florida database. It's kind of analogous to Caltech 101. This is 101 video action categories. So Wesley at the moment has applied it to 6 of them, but he picked 6 tough categories. So he picked, breaststroke versus crawl, putting on makeup versus putting on lipstick, cello versus guitar. Again, things obviously easier for us, but problems that would be difficult for for just a bag of features approach, for a static dictionary to solve. And what he's showing here is the classification. So it's color-coded. You can see that so we had to train 6 different single-layer perceptrons. So we have a very, very simple classifier because we really want to see how our representations are. We want to see if our representations are giving us essentially a linearly separable classification task. We don't want to put all the effort into the back end. And you can see he's doing a pretty good job. He's actually getting 90% correct on these 6 categories without too many confusions. So I was hoping to show you, the next slide would be, in theory, that he did a control where he just used the same number of static dictionary features, and the dynamic features did better. Unfortunately, his control worked really well. And so we're still going to have to track that down. But still, I think this is an exciting direction. It certainly points out the relevance. So what's the time here? Am I completely out? I got 1 minute. Okay. So this is something else Wesley did. I think is pretty darn clever. So these spatial temporal dictionary elements are forced to reconstruct 4 video frames. That's what they do. That's what they know about, right? They're not just a patch, they're 4 patches that occur in sequence. So what Wesley did is he only let the dictionary see, he only let the sparse encoder, in this case spatial temporal sparsity, he only let it see 3 frames. He didn't show it the 4th frame. The 4th frame, there was no error feedback from the 4th frame. So the third column here shows a movie that's entirely predicted. All right, so the first 3 frames are the first 3 frames in this movie were actually seen, but the 4th frame was predicted. So it shows that the spatial temporal dictionaries, well, in some sense, can predict some aspect of the future. And so Wesley and another student who just joined the group, Brian Broompeltz, who's not local, he's from New Orleans, and so they're working on trying to formalize this idea. They're trying to work on actually using these spatial temporal sparse autoencoders to actually predict the next frame. And so my dream for this is to actually build a dream machine, right? Because if you can predict the next frame in a sequence, well, you can make that predicted frame your input if you want to. And then I don't know, right? Then anyway, but that should be fun. So the final application is just going back to Shen Lundquist. So when he's not putting code on multiple GPU spot instances in the Amazon cloud, he's working on. So he's taking the same cortical processing, the same basic sparse autoencoder, but in this case he's applying it to stereo imagery. Okay, so he's applying it to. So now each sparse autoencoder now has to reconstruct 2 patches, one from the left camera, one from the right camera. okay, but it's the same module. And so what he learns, as you might expect, but still it's awfully amazing to see it happen, is he learns dictionary elements that have localized orientation selectivity, as we've come to expect. But his dictionary elements are, whoops, I gave away the punchline. His dictionary elements are disparity selective. They are tuned to this left-right stereo disparity. And if in the bottom panel, what he's done is he's made an average depth map. So this is this data is from a self-driving car project, the Kitty project at the Karolinska Institute. And so they have LiDAR data that's registered with these images. And so he can construct an average depth map every time each one of these binocular dictionary elements is active. And in fact, the depth maps make sense. When he trains the dictionary element at a small spatial scale, it has small disparities. It corresponds to objects that are far away. It's they don't move very much. The disparity is low. And you can see and likewise, big disparities correspond to objects that are nearby. And you can see all of his depth maps tend to flow from dark to light. That means from near to far, which makes sense, right? The stuff down here tends to be close to me. The stuff up there tends to be far away from me. And so he's captured that. So the final slide then is Shen pulled it together. He trained a single layer perceptron again as a depth classifier. He did not use any information about where he was in the image. So there is one depth classifier that applies everywhere in the image. So we're not using any prior. This problem wouldn't be as hard if you knew that you were at a part of the image that was almost always the street, or a part of the image that was almost always up in the sky. And you can see that with just a single level of binocular dictionary elements, again, using the same cortical processing module that we used for all the other tasks, he actually is doing a pretty good job. So I'll just end with, I'm not going to go into details on this because I don't understand the details, but my collaborators at the University of Michigan are implementing this cortical processing module, the one I described, on an ASIC, and eventually we'll couple that with a memristor crossbar. And I don't understand how it works, but I do understand that the specs that they report are pretty astonishing. But I think some similar specs have been reported here. But things like a couple hundred milliwatts of power. But this cortical processing, this chip is actually doing everything I just told you. It is learning a sparse predictive code of its input, starting with random weights, and generating a sparse representation from that optimized basis. So the fifth principle of the third wave of neural computing is that we have to be able to put these cortical processing modules on custom chips. And so anyway, I think we're part of something extraordinary that's happening. I think this third wave is the right. I'm jealous of my students. I think they're hitting this at exactly the right moment. Okay, well, thank you.
So one of the things about the way NICE is scheduled, we don't have the little round table on Wednesday. So I'm going to force you to kind of be provocative here. So you described kind of a universal cortical module concept, but everything you talked about seemed to be sensory processing. And I'm going to call you out on that. Most of the brain, or especially when we start pushing neural computation into cognitive function, isn't just visual processing. So how do you see this idea translating into decision making, motor control, etc.?
That's too hard a question. But it's a great question. Of course it is. All right, so I amend my list. There has to be a sixth element at least. A cortical processing module. So I think Gary Marcus is dead wrong. I think he proposed the worst idea I've ever heard at a meeting, okay? That somehow the cortex is this, that one part of the cortex has nothing to do with another part of the cortex. We can't generalize at all. I hate that idea. But I kind of like his example of the FPGA notion that you could. So to me, the gates in an FPGA are the cortical processing module. That's really what we mean by the gates. And we can wire them up different ways, and different parts of the different parts of this cortical FPGA have different functions. Because I don't work in the motor system and know nothing about it, I don't think the motor system is fundamentally different than the sensory system. I guess that's my answer. I think it has the same basic problem, just upside down. That, in the visual system, we have to take a bunch of low-level features and put them into some high-level concept. In the motor system, we have to take some high-level concept, like, click my mouse, and translate it into low-level actuators. But it's the same problem. And once we realize that another criticism of the module I described here is that it had no top-down connectivity. It wasn't like O'Reilly's Libra, right? So that's something we need to have. We need to have these modules need to work both with top-down and bottom-up input. And so I think at the point a cortical processing module is affected as much by its top-down expectations as it is by its bottom-up input, it's not that much different from a motor processing module. Okay, so that would be my answer. Okay. Okay, thanks a lot.